Okay, do me a favor. Take a deep breath. That air filling your lungs right now, the pressure that keeps your tires firm, even the huge weather systems that swirl around our planet, they're all run by the secret life of gases. In this explainer, we're going to pull back the curtain on this invisible world and figure out how it all really works. So, what do these three things, your lungs, a weather balloon, and an airbag, actually have in common? Well, it turns out they're all governed by the exact same simple, predictable physical laws. And believe it or not, by the end of this, you're going to see exactly how the air in your lungs is fundamentally connected to the way an airbag saves your life. So here's how we're going to break it down. We'll start big with the properties we can actually see and feel. Then we're going to zoom all the way down to the microscopic level to see what the molecules themselves are up to. And finally, we'll see where our perfect, neat little model smashes into messy reality. All right, so what really makes a gas a gas? I mean, how is it different from a liquid or a solid? It really just comes down to a few unique properties that, honestly, we see and feel every single day. Unlike a solid or a liquid, gases have three main party tricks. First, they expand to fill any container you put them in, any space at all. Second, you can compress them, like a lot. And third, they mix together perfectly. The air you're breathing right now, it's a totally seamless soup of nitrogen, oxygen, and other gases. Just try getting oil and water to do that. It's not going to happen. And because gases are always trying to expand, they create pressure, this constant force pushing on whatever surface they touch. Have you ever sucked all the air out of a plastic water bottle? It just crumples, right? Well, that's not the plastic failing. No, that's the massive, invisible pressure of the atmosphere on the outside just crushing the low-pressure space you made on the inside. That is gas pressure in action. So for a long time, scientists started noticing something weird. No matter what gas they were looking at, oxygen, hydrogen, whatever, they all seemed to follow the same set of simple, predictable rules. And these became known as the gas laws, the absolute foundation for understanding how they behave. And these are the big three. First up, Boyle's law. It just says if you crank up the pressure, the volume goes down. That's exactly how you breathe. Your diaphragm changes the volume of your lungs, which changes the pressure, and that pulls air in. Then there's Charles's law. Heat a gas up, and its volume gets bigger. That's literally how a hot air balloon gets off the ground. And Avogadro's law is the one we all know intuitively. Add more gas, the volume increases. It's just blowing up a balloon. Now, what made Robert Boyle's work such a game changer wasn't just what he found, but how he found it. See, he wasn't just looking at stuff happen. He was one of the first scientists to methodically control one thing, the pressure, to see exactly how it affected another thing, the volume. And that's how he uncovered this beautiful, simple inverse relationship. Okay, so we've got these separate rules, right? One for pressure and volume, one for temperature and volume. But what if we could smash them all together into one single, powerful master equation? One that connects pressure, volume, temperature, and the amount of gas, all at the same time. And here it is, PV equals nRT. The ideal gas law. Seriously, think of this as the ultimate cheat code for gases. It takes everything we just learned and rolls it into one. You've got pressure and volume on one side. They have that inverse relationship. And on the other side, you have the amount of gas, N, and the temperature, T, which both have that direct relationship with volume. That R in the middle, that's just a constant that makes the math work out. With this one equation, you can predict the state of pretty much any gas. It's incredible. And this is not some abstract thing for a textbook. This equation literally saves lives. Think about an airbag. In a crash, a sensor triggers a chemical reaction. That reaction instantly creates a very specific amount of nitrogen gas. That's our N. And then the ideal gas law kicks in and dictates the exact volume that gas needs to inflate to. It all happens in a blink of an eye, creating a perfect cushion. It's just a stunning example of physics and chemistry working together flawlessly. Okay, but why? Why do these laws work? Why does PV equal nRT? I mean, what's really going on? To get that answer, we have to shrink down, way, way down, and see what the individual gas particles are actually doing. Welcome to the world of the kinetic molecular theory. So the theory is built on a few simple but powerful ideas. I want you to picture a box filled with zillions of tiny hyperactive billiard balls. They're just zipping around in every direction, totally random. They're so small that their own individual size basically doesn't matter. They don't attract each other, they don't stick together, and when they slam into each other or the walls of the box, they bounce off perfectly without losing a single bit of energy. Now, this model gives us a totally new way to think about temperature. It's not just a number on a thermometer anymore. No, it's a direct measurement of how fast those little particles are moving, their average kinetic energy. So when you heat a gas up, you are literally making its particles move faster. And pressure? Well, that's just the combined force of trillions of these particles constantly smacking into the walls of the container. Faster particles mean harder, more frequent collisions, which means higher pressure. It all just clicks into place. And check this out. Here's a really cool consequence of this whole theory. If temperature is all about motion energy, then for two particles to have the same energy at the same temperature, a lighter particle has to move way faster than a heavy one. This is exactly why a helium balloon from a party deflates so fast. The tiny, super light helium atoms are moving at incredible speeds, so they can easily sneak out through the balloon's microscopic pores. Meanwhile, the much heavier nitrogen molecules in the air around it are just lumbering along, too slow to escape. Okay, so this kinetic molecular theory and the ideal gas law, they are amazingly powerful. But, and there's always a but, they're based on a simplification. They describe an ideal gas that doesn't really exist. And real gases in the real world, especially when you push them to the extremes, well, they start to bend the rules. So let's just look at the data for a second. The ideal gas law predicts that 1 mole of any gas, doesn't matter which one, at standard temperature and pressure should take up exactly 22.41 liters of space. But now look at real gases, like chlorine and ammonia. I mean, they are incredibly close, but they're just a little bit off that perfect ideal. So what gives? What causes that tiny little difference? So why don't they behave perfectly? Well, it comes down to two of those assumptions from our ideal model that aren't quite true in reality. First, real gas particles do actually have a tiny bit of volume. And second, they do have really, really weak attractive forces between them. Now, under normal, everyday conditions, these two things are so small they basically don't matter. But if you crank up the pressure or drop the temperature way down, they suddenly start to become important. And that brings us to the really practical takeaway here. For almost everything we do in our day-to-day lives, as long as the pressure stays below about 10 atmospheres, those tiny little deviations are pretty much negligible. Our ideal model is more than good enough. It's a perfect example of a scientific model hitting the sweet spot, giving us incredible predictive power without getting totally bogged down in the messy, complicated details of reality. And that leads us to our final and maybe the most important question of all. We've just established that the ideal gas law is exactly that, an ideal, a simplification. No gas in the real world behaves this way perfectly. So, why is this one simple equation, PV equals nRT, still one of the most vital, most essential tools in all of science? Well, the answer tells us something really profound about the true power of a good model. Thanks for joining us on The Explainer.